world. I'm Jared. If you're new here, I'm a Rubyist. I run an agency called Super Good Software where we build e-commerce systems using Ruby on Rails and a platform called Solidus. We have finally reached day 25 of the Advent of Code for 2021. I've just finished day 24 after struggling at length with having not actually been returning from one of my methods. Yeah, that's how today's going, but we're on the final day, day 25. Let's get it wrapped up here. This is it, the bottom of the ocean trench, the last place the sleigh keys could be. Your submarine's experimental antenna still isn't boosted enough to detect the keys, but they must be here. All you need to do is reach the seafloor and find them. At least you'd touch down on the seafloor if you could. Unfortunately, it's completely covered by two large herds of sea cucumbers, and there isn't an open space large enough for your submarine. You suspect that the elves must have done this before, because just then you discover the phone number of a deep-sea marine biologist on a handwritten note taped to the wall of the submarine's cockpit. Sea cucumbers. Yeah, they're probably hunting for food, but don't worry, they're predictable critters. They move in perfectly straight lines, only moving forward when there's space to do so. They're actually quite polite. You explain that you'd like to predict when you could land your submarine. Oh, that's easy. Then they'll eventually pile up and leave enough space for... Wait, did you say submarine? And the only place with that many sea cucumbers would be the very bottom of the Mariana... You hang up the phone. There are two herds of sea cucumbers sharing the same region. One always moves east, while the other always moves south. Each location can contain at most one sea cucumber. The remaining locations are empty. The submarine helpfully generates a map of the situation, your puzzle input. For example, every step, the sea cucumbers in the east-facing herd attempt to move forward one location. Then, the sea cucumbers in the south-facing herd attempt to move forward one location. When a herd moves forward, every sea cucumber in the herd first simultaneously considers whether there is a sea cucumber in the adjacent location it's facing, even another sea cucumber facing the same direction, and then every sea cucumber facing an empty location simultaneously moves into that location. So, in a situation like this, after one step, only the rightmost cucumber would have moved. After the next step, two sea cucumbers move. During a single step, the east-facing herd moves first, then the south-facing herd moves. So, given this situation, both sea cucumbers on the right hand have moved, blah, 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 blah. Due to strong water currents in the area, sea cucumbers that move off the right edge of the map appear on the left edge, and sea cucumbers that move off the right bottom edge of the map appear on the top edge. Sea cucumbers always check whether their destination location is empty before moving, even if that destination is on the opposite side of the map. To find a safe place to land your submarine, the sea cucumbers need to stop moving. Again, consider the first example. Okay. What is the first step on which no sea cucumbers move? Okay. Seems straightforward enough. So this is our example. Give us an initial state. We can use... Okay, in there. They tell us that it should be part 1, it should be 58. Input strip. Split on new lines as usual. each with index, line. This is the index, this is their Y position here. And oh, sorry. And then each line I want to map these, I think. Or flat map these? Flat map these. And then 2H this whole thing. So the lines are going to be split on characters. Each with index. Yeah, these ones we're just mapping them, and it's going to be the character and the x coordinate here. We can compact that. Whoops. Compact that. And so then we want these to each be a pair with an XY coordinate mapped to C. Unless C equals dot. Okay, so let it be nil, it'll get compacted out. So that should give us an initial state. Let's focus our spec that we care about here. Just for fun, we're running YJ on everything. Wrong array length. 0, expected 2 was 1. Let's check that off and see what we're producing here that's so wrong. I can't 2H that? Oh, I see what I did. These are supposed to be pairs, not hashes. Look at that, the other two. Okay. So steps equals 0. Loop do and we reference steps. And the steps we want to have a method with flag. Do stuff, and then trim new state. There's something in my editor that showed trailing white space. It doesn't anymore. I guess next is a keyword, isn't it? Does this matter here? Yeah, it does matter. Plot advance. If new state equals state, then break, else I guess we can just do a little one of those guys. Break if new state equals state, otherwise steps plus equals 1, and we continue. Now it's gonna, now it works. Why is it infinite looping? Shouldn't it after one loop? Oh, I'm not setting state equal new state. Now I'll just immediately exit after applying once. Cool. Okay, that means that our like basic structure for this is working. We just need to do this piece. So we'll go state each. I guess we want to advance. So let's check the puzzle again here. The wording is correct. East moves first, then south moves. So we'll want to do east first, then south. So what does that mean for us here? What does this mean? We need to loop over the ones that are east movers, move them, then loop over the ones that are south movers. So state dot select position each. Try this. Oh, this works. We'll find out. Amazing. We actually need to record the size of this thing here. So height is going to be I guess we can assume that any given input, the max x and the max y, are going to be the height and the width. So height is then going to be date dot keys dot map last dot max, and width state keys map first dot max. Very scientific. So destination x is going to equal x plus 1, dx equals 0 if dx is greater than or equal to width. I'm moving y. Next, if so, there's already something in the xy. Otherwise, it's not. So in new state, we set x y equals c. That seems like it would move the east ones. I guess we can move. I guess we don't need to do this. You know, if C is this, then we do this. Otherwise, we just don't move. And then we do this again. So we say state equals new state equals that. Now we're doing it for these. These are y's, right, x and dy, x and dy. That's kind of like it might work, but it doesn't. Hilarious. Great. We can debug this though. So that's pretty easy to debug because we've got an example and we can just walk. No, that's not an example. Harder example. We've got this, we can walk through it. We just need to be able to print this thing. Zero. So we just need a I should be able to pass the state in for this. State x, y, or dot. Join those. All right, print new state. Okay, well, I'm confused. Doesn't look like doesn't look right good. Okay. This is our input. So we're expecting this one to move down into here. That one did move. Maybe we can. So let's just say. I don't need that. I can just put on do it in here. So initial state looks normal. I guess I can make this more. So look at things. So this should move over. Yeah, this is totally whack. So that one shouldn't have moved. It got completely eaten. This one did move over. So something's really wacky here. Oh, I see what's happening. They're disappearing. Just getting totally eaten up. We'll get there. We'll figure out how to spell. Okay, now we're getting right looking result. Not quite. But almost. How am I getting? So, this one should move down. It does. This one should stay where it is. It does. This one should move down. It does. This one should move over. This one should move over. That one should stay. What do we got here? So that one should become occupied. That one, not so much. Something's wrong though. Is there something wrong? I'm missing this one. For is my initial state wrong? Oh, my width calculation's wrong. Okay, yeah, no, that looks like it's working. All right. We have an off by one. Suddenly, the experimental antenna control console lights up. Sleigh keys detected. According to the console, the keys are directly under the submarine. You landed right on them. Using a robotic arm on the submarine, you move the sleigh keys into the airlock. Now you just need to get them to Santa in time to save Christmas. You check your clock. It is Christmas. There's no way you can get them back to the surface in time. Just as you start to lose hope, you notice a button on the sleigh keys. Remote start. You can start the sleigh from the bottom of the ocean. You just need some way to boost the signal from the keys so it actually reaches the sleighs. Good thing the submarine has that experimental antenna. You'll definitely need 50 stars to boost it that far, though. The experimental antenna console lights up again. Energy source detected. Integrating energy source from device sleigh keys done. Installing device drivers done. Recalibrating experimental antenna done. Boost strength due to matching signal phase 1 star. Only 49 stars to go. You have enough stars to remotely start the sleigh. You use all 50 stars to boost the signal and remotely start the sleigh. Now you just have to find your way back to the surface. Did you know crab submarines come with colored lights? Huh. Well, it's been a journey. We got there yet again. It's nice that it wasn't anything too tricky on day 25 here. But that's it. If you came out, watch some of the videos. Thanks for doing it. Follow me on Twitter or whatever. I'm not super active on Twitch outside of December's, so that's where you can follow me. But see you, everyone.